You'll want to be able to claim your CMEs, please do so at the end of the event. Any questions that you may have for our speaker, please put them in the chat. I will be moderating, and at the end of the presentation, we'll do a Q&A. And so it is my pleasure to introduce to you Dr. Thomas Francisco Jaramillo. He is a professor in our Department of Chemical Engineering here at Stanford University. He in Energy of Science Engineering here at Stanford University, along with his faculty appointment at Photon Science at SLAC National Accelerator Laboratory. He serves as a director for SUNCAT Center of Interface Science and Catalysis, a joint partnership between Stanford and SLAC. Dr. Jaramillo's research efforts are aimed at developing catalyst materials and new processes to improve sustainability in the energy and chemical sectors. He has a key emphasis in engineering catalyst materials at the nano and anatomic scale to induce desired properties, and then on designing and developing new technologies that employ them. Examples of this include both solar and wind powered processes to convert both CO2 and nitrogen into valuable molecular products such as hydrogen and ammonia-based fertilizers and carbon-based products such as fuels and plastics for use in both transportation, agricultural, energy storage, and in the chemical industry, among others. There's an overarching theme here in the development of cost-effective clean energy technologies that can benefit society and provide for economic growth in a sustainable manner. Dr. Jaramillo has authored over 200 publications in the peer-reviewed literature in these areas and has earned a number of honors and awards for his efforts. Honors include the Paul H. Emmett Award in Fundamental Catalyst from the North American Catalyst Society, the Resonate Award from the Resonate Institute, the Presidential Early Career Award from Scientists and Engineers, the U.S. Department of Energy, Hydrogen, and Fuel Cell Program Research and Development Award, the National Science Foundation Career Award, and the More Devout Ventures Innovator Award. He is also an annual list of highly cited researchers by Clarivate Analytics, ranking in the top 1% by citations. Dr. Jaramillo is from Carolina, Puerto Rico. He earned a BS here in chemical engineering at Stanford University and his MS and PhD degrees in chemical engineering at the University of California, Santa Barbara. He then pursued a postdoctoral research as the Hans Christensen Orsted postdoctoral fellow at the Technical University of Denmark, Department of Physics, prior to joining the Stanford faculty. So it is my pleasure to welcome, as he said, Tom, but Dr. Jaramillo.
Thank you so much, Sabrina, for the kind introduction. Thank you, and thank Lisa for the opportunity to participate, the invitation to participate. This is going to be a little bit different probably than some of the other seminars that you've been part of over the past many months. I'm going to try to make some connections, certainly, to the medical community. I'm not a medical doctor by any stretch, but I think there are some broader topics of sustainability that are absolutely essential for everybody to be thinking about, including in the health sector. And I have a few more words I want to say about that in a moment. But the general theme is global sustainability, and there's a lot happening in our world, and especially here at Stanford campus. I want to touch on that as well. All right, so what I'd like to start with is, I'm a chemical engineer, as Sabrina pointed out a moment ago, chemical engineer by training. And when I started off as a chemical engineer, before I started off as a chemical engineer, I had no idea what is a chemical engineer. And I thought that might be helpful to kind of give a sense of, what we're trying to do in our field. And the way I want to bring it up is to bring up a certain molecule that we touch every single day of our lives. It's hugely important. It's a manufactured species. We don't just find what we need from the air or from the ground. So we actually have to create it and synthesize it. And it touches billions of people on Earth, and it's part of you right now. And what I'm talking about here is fixed nitrogen, and more specifically, ammonia. And this is one of the greatest examples of chemical engineering. When it was discovered over a century ago, it was found that there is not enough fertilizer on Earth to support the growth of the human population. All the fertilizer that was used at that point was really coming from natural sources. So we all probably learned in grade school and high school about the natural nitrogen cycle, and through lightning, for instance, that's enough energy to split the nitrogen bond end, molecular nitrogen. This is, of course, this is the number one component of the air that we're all breathing right now. 78% of what we're breathing is N2. And that is one of the toughest bonds in all of our universe, all of our known universe. And so it really takes a lot of energy to split that thing and turn it into a fixed form. Why is that important? Because fixed nitrogen is what proteins are made of. It's what DNA is made of. It's what enzymes are made of. These are absolutely essential biomolecules for us and so many other species. And the question is, how do we get that fixed nitrogen into our body? And again, a century ago, it was realized that there wasn't enough natural nitrogen to go around, natural fertilizer to go around to make that happen. So it's one of the greatest revolutions really in technology that benefits humankind. It's the process that we're looking at here. If you look to my right, this is an iron nanoparticle. You can tell it's a nanoparticle. You can actually see, well, first of all, the dimensions. This is 5 nanometers. This is a transition electron microscopy image. You can actually see the lattice fringes of that iron nanoparticle. And thanks to this nanoparticle and many others just like it that are scattered across the globe in facilities that are called Haber-Bosch production facilities, they take in nitrogen from the air, they separate it from the air, they grab hydrogen, usually from natural gas, they basically strip the hydrogen off of natural gas, and they react this on this iron nanoparticle to make ammonia. And look at the scales, 180 billion kilograms a year production of ammonia. And if you average over the 8 billion people on Earth, that's over 20 kilos per person per year. That's 50 pounds of ammonia is what each of us demands in order to sustain life. Half of the fixed nitrogen in your body right now touched one of these iron nanoparticles somewhere around the globe where this reaction took place. The ammonia goes out the plant gate. It takes on different forms in order to fertilize the ground. Once you fertilize the ground, then you can grow the crop. And then we either eat that crop directly, or maybe we eat an animal that ate that crop. That's how we get the fixed nitrogen into our body. And this is a chemical engineering problem where it took a really good understanding of how to drive a very difficult chemical reaction such as this one, just as step A. And then step B, how do you scale it up to literally feed billions of people across the globe, including all of us here today? So this is the breakfast that you ate this morning, the dinner that you had last night. All that fixed nitrogen that went into the ground came from iron nanoparticles just like these, and that's how we can live and thrive. But there's a problem. As amazing as this process is, it is completely unsustainable. And that's just one of many, many, many examples of how we need to change what we're doing if we want to live sustainably. And that's really the theme of what I want to talk about today. This is a marvelous process, and yet we have to reinvent it from the ground up. This process and so many others. So this all comes down to so many challenges in sustainability, and climate is, of course, a big one. It's not the only one, but it's a big one. And I want to just kind of touch base with, for those of you who are health professionals, why is this important? And there are a lot of reasons why. At the end of the day, when you have climate change, that poses additional health risks than we're already accustomed to. And so you can see this particular slide, this image came from the World Health Organization. You can see what are some of the climate-related hazards and how that can lead to certain groups being more vulnerable than others. There's different exposures to different parts of our ecosystem with different health outcomes that only add more pressure onto our system. So it really behooves us to think about how we can combat climate change for many, many reasons, including for the health risks that are involved. Many drivers here. This is another chart I wanted to show you, and I'm happy to share my slides with you afterwards that has all the links. This one's coming from the Pan American Health Organization, which is part of the World Health Organization umbrella. And this one has a more granular view into some of the health impacts of climate change, things that we need to anticipate, things that we need to be adaptable and be ready to address. And I want to point out in particular, as particular reference, Climate Change for Health Professionals, a pocket book that really unpacks a lot of these challenges. These are challenges that we are going to see. There's no two ways about it. We're already seeing it, and it's frankly only going to get worse in the near future. And that's why people like myself and many others from coming across all sectors, including the health community, we have to work together to find solutions and find them fast and develop them at scale. Because if we don't address these problems at a global scale and do it soon, it's going to be even more challenging ahead. So I'm going to say a few more words about that later on, but wanted to connect to some of the acute issues that we are already facing and will continue to face thanks to climate change, unfortunately. So if we want to understand how we want to combat climate change and how we want to improve sustainability, it's important to take a view into global energy as we know it today. And so I just want to set the story straight just to make sure everybody knows exactly where our energy comes from. And this is a plot. This is another really good reference. The International Energy Agency, it is one of the most reputable sources out there of really a number of different governments coming together, providing resources, industry as well, analysts, economics, et cetera, to understand where the energies are flowing across the globe. And this plot shows you some of the key primary sources of energy and how that's changed over the years, going all the way back to 1971. And what you find is the energy mix hasn't really changed that much over the past half century. And despite great advances in wind technology and solar technology that are getting deployed really fast these days, it's still, frankly, a drop in the bucket compared to the conventional energy. So you can see in 1973, this was the mix. About a little over 80% coming from fossil fuels of coal, oil, and natural gas. In 2019, it was still about 80% coal, oil, and natural gas, although you can see there's a shifting trend as to which fossil fuels are being used more than others. Clearly, natural gas is on the rise. So good numbers to just remember is that about 80% of our energy supply today comes from fossil fuels. That's still true today as it was 20 years ago, as it was 50 years ago. And the ratio of oil to coal to natural gas these days is about 1 to 1 to 1. And things haven't changed that substantially over the years. But things are starting to change. And I'll talk about that for sure. But before I do that, I'd like to say a few words as to why fossil fuels are such the dominant source of energy. And on this slide, I just want you to have in mind gasoline or petroleum as the example. First and foremost, it's a massive worldwide resource. So we use about 19 terawatts of total power on average, okay? 19 terawatts, 19 trillion watts of joules per second, okay? That's what a watt is. And about 5 of those 19 terawatts is coming from just oil, just petroleum alone. So it's a massive worldwide resource, extremely abundant. 20 years ago, there was a lot of doom and gloom in the United States because natural gas production was dropping, oil production was dropping, but really due to technological innovations in that space in the oil and gas industry. This is in fracking, this is horizontal drilling, this is advances in drill bit technology. Based on all of that, now the USA is #1 in both natural gas and oil production worldwide. So there's a lot of it, and we're not going to, as they say, the Stone Age didn't end because people ran out of stones. They came up with a better technology, and that's what got us into the Bronze Age. The fossil energy is certainly there for us for the taking, and unless we do something different deliberately and proactively, we're going to continue using it. It's also got a tremendous energy density and a tremendous power density. You don't think much about it, but when you hop in a car, you can drive 400 miles on 1 tank of gas, or even fly from San Francisco to Frankfurt on 1 shot with 300 friends around you. If you want to calculate how much energy is in your car's gas tank, it's equivalent to about 30,000 iPhone 15 batteries. Pretty impressive. And then it's got high power density, which means not only do you have a lot of energy storage on board, but you can power just about anything you want. It can be automobiles, trucks, massive shipping vessels going across the Pacific, et cetera. And you might not think too much about it when you're at the gasoline pump, but when you're standing there looking bored, filling up your car, it's about 5 megawatts worth of power flowing through your fingertips. So if you have 200 people looking bored at a gasoline, several gasoline stations, that's equivalent to a nuclear power plant's worth of energy flowing into their vehicles. That's how much energy is stored in the chemical bonds of fossil fuels. And yet it's all very chemically stable. You probably hop in cars and buses, you're not worried about it igniting and exploding on you. And that's because despite the high energy density, we've been able to make them very safe. That's really an engineering challenge. It's also very easy to store and transport. 100,000 miles of gasoline pipeline in the United States. It might get refined in Houston and get sent all the way over here or sent to the Northeast. Can be, as a liquid fuel, can fit into any shaped container. And then if you think about gas prices today, they're not cheap. It's $5 a gallon. But when you really think about it, how does it compare to other consumer goods? How much does a gallon of bottled water cost? How about a gallon of milk or a gallon of orange juice? And so when you think about that, driving to Stanford or San Francisco for $5 worth of energy, that's not bad at all. And then there's the convenience and the scale. Of course, you can find this all over the earth, distributed, supply chains, transportation, et cetera. And while most of us probably don't enjoy stopping at a gasoline station to fill up, I encourage you to time yourself at the gas station. The instant you pull the lever on the nozzle to the time you take it out, probably about 3 minutes. And that's it. Imagine if your iPhone was fully discharged, you're in an airport, you're rushing to find an outlet, and you plug it in for 3 minutes. How much charge would you get out of that thing? So pretty impressive set of properties. And the reason why I want to bring this up is for us to recognize how amazing that resource is, and B, if we want to come up with future energy technologies, we're going to have to compete with those attributes. So just to speak a little bit more about the chemistry behind it, all those molecules are really the broader class of hydrocarbons. And so when you're turning on your gas stove here in California, it's predominantly methane is what you're burning. So it's CH4, it's just one of many hydrocarbons. And all these hydrocarbons are very similar in molecular structure. They're all carbon and hydrogen, hence hydrocarbons. And as you make the chains longer, going from, say, methane to ethane to propane to butane, these are all typically gases at standard temperature and pressure. You get them, when the chain is a little bit longer, it turns into things like gasoline or diesel or jet fuel. And ultimately, when it's long enough of a chain, it becomes motor oil, which we use to lubricate engines. So interestingly, it's really this one broad class of molecules that we get from underground. And all we do is refine it a bit, and then we can turn it into all these different types of products that we use every single day. It's no surprise that this is the dominant energy source. It is extremely inexpensive. Mother Nature spent the time making it over millions of years. We basically stick a straw under the ground, pull it up, and refine it a little bit, and it's good to go for so many different applications. That's why this has been the dominant energy carrier for decades and decades and decades. Now, there's, of course, many problems with that, and we're coming to realize that more than ever, and CO2 emissions is just one piece of the puzzle. And so this is coming from, again, the International Energy Agency, a more updated version of their Key World Energy Statistics that they publish every single year. And you might be aware that we're cranking out about 40 gigatons of CO2 per year. And you can see where we've been historically. This is a blip during the COVID times, and then back up again, right? Kind of continuing as we used to before. And what you're looking at are 3 forward scenarios for what might happen to CO2 emissions. And we realize that we'd better do something soon, because otherwise the temperature of the globe is going to keep climbing and get out of control, maybe irreversible effects, and certainly have disastrous consequences on communities. So we'll talk more about temperature rise in a second, but let me tell you what these 3 scenarios are. STEPS is stated policy scenarios. So if you look at the policies that are on the books in industry and governments worldwide based on trying to mitigate CO2 emissions, this is what's going to happen between now and the year 2050. APS is the announced pledges scenario, where if you take every country's like pledge, the Paris Accords and all of that, and the IPCCs, and everyone's saying we want to do this and we pledge to do that. Okay, those aren't policies on the books yet, but those are pledges, which are definitely not as enforceable. But this is what it would look like. And then this is the net zero emission 2050 scenario. This is the most aggressive of the bunch. And it's kind of hard to imagine that we might be able to make such a sharp pivot and go down this pathway, but it's good to see what that looks like and then translate that to temperature rises. And so these are the median temperature rises under these 3 different scenarios compared to historical averages. And you can see even under the net zero scenario, we're talking about, a 1.5 or so degrees centigrade increase is the median. If you go to the APS scenario, it's closer to 2. And once you're in the STEPS scenario, which is, again, those are the policies in the books, you're north of 2 degrees. But I want to remind everybody, first of all, these are degrees C, not degrees Fahrenheit. So it's close to 2 to 1 ratio there. The other thing is that look at the spread. Remember that not everyone in the globe is going to be affected in the same way. And so while these are the medians, and those are oftentimes what are cited and what are tracked, there's going to be this very long tail of people on this globe who are going to feel a much, much greater increase. And that's just going to cause more drought. It's going to cause challenges to nutrition. And as we all know, nutrition has a direct correlation to health and so many other factors, that this is really what the scary part is. And so all the 3 of these scenarios, while they don't look particularly optimistic in terms of the temperature rises, recognize that even the STEP scenario has a downhill in terms of our CO2 emissions, which really puts the pressure on us to figure out how we can improve technology and society, frankly, and operate in a different way so that we're trying to stave off the worst effects of climate change. As a friend of mine and colleague in the School of Sustainability, which I'll talk about in a second, mentioned to me, there's only 3 responses to climate change. There's mitigation, there's adaptation, and there's suffering. So what can we do on the first 2 to ease the third? All right, now this has been a focus on energy and a focus on CO2 and a focus on temperature rise, but sustainability is not just about energy. And so what I wanted to show you here is really, this is the United Nations Sustainable Development Goals, where they've come together, experts have come together and really identify kind of crisp areas that we need to address very proactively to have global sustainability. And I think they're worth walking through it for a moment here. So no poverty, 0 hunger, good health and well-being, quality education, gender equality, clean water and sanitation, affordable and clean energy, decent work and economic growth, industry, innovation, and infrastructure, reduced inequalities, sustainable cities and communities, responsible consumption and production, note the circularity, climate action, life below water, life on land, peace, justice, and strong institutions, and partnerships for the goals. You look at this slide and everybody on Earth can help contribute, no matter what your discipline is, no matter what your background is, there's opportunities to contribute on all of these. And some of these are directly related to the energy problems and the CO2 problems that I was talking about, but many of these aren't. And there are correlations across the board, which really says, how can we reinvent how we work together? How can we reinvent how society functions? As an engineer, I used to think that I could solve any problem if I came up with the right technology that was greener, cleaner, faster, cheaper, better. But then you realize that it's not just about the technology that we need to engineer, which is important. It's really all of society that we need to re-engineer. And again, all of these things are correlated to one another in one shape or another. And so we really need to think about this holistically. So what's Stanford doing about it? So you may have seen an announcement that came out in May of 2022. This is almost 2 years ago that Stanford launched the Stanford Doerr School of Sustainability. This is a picture of Ann and John Doerr. They were kind enough to donate $1.1 billion to found the school. There were a number of other families that added donations to bring it up to $1.69 billion with the B. And I have never seen any university on Earth do something like this. So this Stanford Doerr School of Sustainability, it's the first school that Stanford started in over 70 years. And it is on par with all the other schools that make up Stanford, right? We've got a fairly decentralized system here where, yes, we all roll up to the university called Stanford, but we have a school of medicine, and we got a law school, and we have a business school, and we have a school of engineering, and we have a school of education, we have a school of humanities sciences, and we've got a school of sustainability. So it is on par with all the other schools. And this has been really important because this new school that just started about 1.5 years ago formally, the deans of each of these schools have what I call superpowers. And that really allows a school to operate with a business model that makes sense for the goals of that particular school. So this is not an institute. This is not a center. This is not a department. This is a school. And that is a really, really strong organizational structure to make change and do things differently than a typical school might have, for instance, the School of Engineering, which I also have a footprint in. So this is one of the most exciting things to happen to Stanford in a really long time. And the whole goal of this School of Sustainability is really to bring the community together. So that's Stanford scholars across all areas of sustainability. We just saw 17 of the UN challenges to reach a sustainable globe. And we're going to need all of these areas to make the desired progress. And really what the school does is it provides a connective tissue where under one roof with a business model that looks different from the other schools, these scholars can work together in climate, energy, human dimensions, health, food, water, ice, ocean, atmosphere, etc., so that we can come up with what I call a goal to say 2050, where we're considering all of these factors, the finance, the markets, the policies, the sociology, the technology, medicine, health, oceans, atmosphere, earth, etc., You have to take all of these things into account to come up with a solution that works for everybody, with a goal, with a north star that we can all strive towards, and know that as we each ply our trade in our respective disciplines, that when we reach our goals at the individual discipline level, they also cross connect with all the other goals. So you actually have a fabric that connects together, and it all can work together as one. So that's really the goal of the new school. Now, one of the cool things about the school is that it has also something that I have never seen at a university, and that's an accelerator. It's called a sustainability accelerator. And at a university such as ours, and this is true of many, many other universities out there, the foundational pillars of why universities exist is really for two major reasons. Number one is education, and number two is basic research. Again, across many, many different disciplines. And so we've got a lot of intellectual horsepower in our community. There's no question about it. And then when we think about sustainability and we think about these massive scales of 19 terawatts of 8 billion people in climbing, people moving out of poverty and into the middle class, right? There are a lot of challenges out there that we need to figure out. So there's a scale that is just immense because it involves everybody. At the same time, there's an urgency. These are challenges we need to solve ASAP, if not yesterday, because otherwise, you saw what the models predict. We're just heading towards a very disastrous consequence if we don't. So how can you take all that intellectual horsepower that we have on a campus like ours that has been really committed to basic research and education, which are super important, and we need more of that, in fact, but we also want to provide outlets for people to really accelerate potential solutions into the real world. So the goal here is, as we come up with a global network across the globe of where we have movers and shakers, some of them from our alumni network, some of them from outside. At the end of the day, we're trying to learn from the globe. What are the challenges across different regions and locations? Have that feed in to the accelerator where we can build solutions teams, people who are interested in participating in this and really not only doing the basic research and education that is foundational to their academic life, but put some of that energy towards coming up with real solutions for real world problems. And so that we can co-develop solutions with the outside world, and through working with different nonprofits and businesses, policymakers, platforms, et cetera, we can try to integrate some of those solutions. And at the same time, really help educate people from all different stages of their careers through a sustainability academy. And that way, the outside world can learn from scholars here who focus on these topical areas and help them move and shake better out in the real world, which is really where it counts. So that's a little bit about what's happening in the School of Sustainability. Now, with my last few minutes here, I just want to provide with you one research vignette that's coming from our research group, just to give you a sense of how we're trying to contribute to all of this. And then, of course, I'd be happy to take any questions and would love to have a discussion with all of you on sustainability in general and how it maps onto your world. And I want to start with kind of these chemical processes that I brought up earlier, such as ammonia production. Ammonia is just one of 70,000 different molecules out there that are essential for doing what we do and to lead a high quality of life. Some other big ticket molecules are hydrogen, where there's about 70 billion a year production rate, or gasoline at about 1 trillion kilograms a year, plastics, of course. And these are just massive scales, very important to do what we're doing. And again, almost none of these are produced through a process that is sustainable. So how can we buck that trend? How can we make the molecules that we need and do so using renewables and do things in a sustainable way? Well, here's the game changer. And I brought this up a little bit earlier, but here's the data to show you the dropping prices of solar and wind power. So you're looking at these plots of unsubsidized wind, levelized cost of electricity. Here's solar PV, levelized cost of electricity. And you can see even just like a decade ago, these were pretty high prices. These are written in dollars per megawatt hour, but they're very easy to convert into cents per kilowatt hour. So back in the day, saying about 10, 15 years ago, wind was about 10 to 15 cents a kilowatt hour, now down to 4 cents a kilowatt hour. Solar 10, 15 years ago was 15 to 30 cents a kilowatt hour. Now it's down to 4 cents a kilowatt hour. And I presume many of you pay your electricity bills and take a look and see what you're paying in your household. 4 cents sounds pretty good. And that continues to drop. And so really this has been a game changer because it says, how can we make use of low cost electricity to power the chemical conversions that we need to make things like fuels, to make things like fertilizers, to make things like building materials and sustainable plastics. And so that's really what a lot of our research program in the SUNCAT Center is all about, where we're really focused on catalysis, where we're trying to do chemical transformations of molecules that we have access to. So all of us are breathing nitrogen, all of us are breathing methane, all of us are breathing carbon dioxide, all of us are breathing water. This is true all over the globe. And the question is, how can we power chemical transformations where you take feedstocks such as these that everybody has access to one way or the other, and use either direct sunlight to power these chemical transformations or to come up with electrified processes to make the chemical transformations. And then you can either make the molecules you want, you can make the fertilizers directly or make the transportation fuels, make building materials, et cetera, or we could make molecular intermediates that we can then feed into the modern fuels and chemicals industry as we know it to then make the products that we want. So this is just to whet the appetite of possibility. There are many, many types of technologies we can imagine on a slide like this one. This just gives a sense of what the opportunity is, where not only do we want to make technologies that can fill the gaps and make these products sustainably, but also how they can interconnect with one another. And that's actually one of the biggest challenges, because the whole fuels and chemicals industry as we know it, which is massive, like I said, 80% of global energy comes from fossil fuels, and we need it. Now that we have these game changers, like dropping prices of electricity, it behooves us to think how we can take advantage of that. And we need, if we're going to develop any one technology, we need to think about the integratedness of, or the integration of all these different types of technologies so that we can lower the costs even further, because that's the world that we live in today. The prices are cheap at the gas pump. If you really think about it, the prices are cheap when we're buying retail items, building materials, et cetera. And that's because it's all highly interconnected. So this is why I work with my partners here at the SUNCAT Center for Interface Science and Catalysis. As was mentioned earlier, it's a partnership between Stanford and SLAC. We're over 70 researchers, all working on catalysis, energy, and sustainability to make the products that we need. Now, the one research vignette I wanted to bring up here was hydrogen. You might have heard a bit about hydrogen. Hydrogen's had an interesting course of history over the last 30 years. It's had some ups, it's had some downs. People say it's the future, people say it's not. People say it's something in between. These are some of the more recent forecasts, thanks to a lot of legislation in recent years in the EU and now in the United States through the Inflation Reduction Act, as well as the Jobs Act. And I just want to remind everybody that the global scale of hydrogen production is already about 70 megatons per year. That's 70 billion kilograms per year. So people can talk about whether it's the future or not, but it's already here. This is a massive scale. And by the way, that production of hydrogen has a stoichiometric amount of CO2 that comes out, because we're getting that hydrogen from fossil fuels, at almost 1 gigaton per year. Mind you, it's about 40 gigatons total. So if we can find renewable ways to make hydrogen and just replace that, we're already putting a dent into the CO2 emissions problem. So these are some forecasts coming from PwC looking into the future as to what possible scenarios might be in terms of scaling up hydrogen, and specifically green hydrogen projects. And so many, many projects have been announced, and we'll see how those go in the future. But these installations are getting built at the gigawatt scale already. Now, do we have the technologies today to scale green hydrogen cost effectively? I've got an answer for you, and the answer is no. So right now, any of those green hydrogen projects are going to be making hydrogen at a cost that is too high to compete with fossil fuel derived hydrogen. So it behooves us to figure out ways to improve the technology, higher performance and lower cost, to make it more deployable. So I just wanted to share with you just a tidbit about hydrogen and what's happening in this space, recognizing that hydrogen is just but one of many molecules that we need. And again, it is commercial. We've been commercializing, we as a society have been commercializing water electrolyzers for hydrogen for almost a century. And here's a 20 megawatt module produced by ThyssenKrupp. And you can see it's about $4 to $5 per kilogram. 1 kilogram of hydrogen has about the same energy content as 1 gallon of gasoline. So $4 to $5 per kilo of hydrogen is about commensurate. But the problem is that this hydrogen, of course, was not made sustainably unless you're feeding it in renewable electricity directly. And right now, the electrolyzers that are deployed, they might sometimes, when the sun is shining and the wind is blowing, they might be using renewables, but they're also connected to the grid and will use conventional power as well. Otherwise, the costs would be exorbitantly higher. Now, the U.S. Department of Energy has announced several Earth shots. This is kind of akin to the moon shot, the Apollo mission that got us onto the moon. That was a very directed effort to make that happen. So the DOE is now calling them Earth shots. Kind of in parallel, there's a number of them. One of them is on hydrogen, where the goal is to get down to $1 for 1 kilogram of hydrogen within 1 decade. Very ambitious goals. And if you look at the techno-economics, this is bread and butter chemical engineering here. This is done by a company called Photon Science. They're located in Connecticut. They sell electrolyzers. They manufacture them and scale them. They're one of the market leaders. They've been procured by Nel, which is the Norwegian electrolysis company, formerly Norsk Hydro. And they've basically they're showing us what a chemical engineering plant facility looks like to make hydrogen with these electrolyzers. You can see the banks of electrolyzers here. You feed in water, you feed in electricity. You need a lot of elements to the plant. It's not just the water electrolyzers doing their thing. And then they're showing us where the costs are coming from for a 50-ton-a-day production facility. And so the point I wanted to make here is really the key thing is that the biggest chunk of the pie, the biggest cost are the stacks. These are the electrolyzers themselves. And a big issue is that they contain precious metals like platinum and iridium. So our research group is really aiming at trying to reduce precious metals into these systems. And so here we go to biology. And so if we take a look at enzymes like nitrogenase and hydrogenase, okay, these are Mother Nature's fantastic catalysts for hydrogen production. And you take a look at the elements here, not a single one of them is precious metal. And so basically biology has figured out a way to make hydrogen very cheaply compared to platinum catalysts that are used conventionally. So these are calculations, these are computational simulations at the quantum level conducted by Jens Norskov and Berit Hinnemann. And this inspired us when I was doing my postdoc in Denmark, as Sabrina had mentioned a moment ago, when I was really inspired by these calculations and that pointed towards certain types of solid state materials that are non-biologic in nature that might have the same type of chemistry on the surface to be able to make hydrogen cheaply without precious metals. This is a material called molybdenum disulfide. So when I was a postdoc in Denmark, we worked in a team to synthesize these nanoparticles of molybdenum disulfide. We showed that they were actually quite good catalysts, non-precious metal catalysts for hydrogen. Started the research group here. And here's Jabo and Jakob, were early stage researchers that joined me on this journey, making nanowires of these materials and nanoporous materials and small molecular clusters. This is a scanning tunneling microscope image. You can see the scale bar 1 nanometer. These are the atoms of these molecular complexes that you're looking at. And as we went from formulation 1 to 2 to 3, we were just improving the catalytic activity of these systems. This led us to a broader class of materials of non-precious metal catalysts that then another 2 researchers in the group, Mackenzie and Laurie, started scaling it up and sending to Connecticut to the company I mentioned earlier, Photon Onsite, where they integrated these catalysts into their real electrolyzers that they sell commercially and show that they actually work in that platform as well. So the catalysts that we synthesized and did basic research in the lab, we were able to translate into real technology for real commercial grade electrolysis units manufactured by this company in the Northeast. Now we've been taking this approach and now applying it to other areas. That was kind of a vignette on hydrogen, but just to give you a sense of where we're taking all of this, we've been doing the same with CO2. Can we capture carbon dioxide from the air and convert it using the same type of electron-driven processes using renewable electricity to make all those carbon-based materials, that whether that's plastics, whether it's the hydrocarbons for transportation fuels? There's a lot of areas that are very difficult to electrify. For instance, long-distance aviation, getting from SFO to London, for instance, SFO to Singapore, SFO to Beijing. How do we do that in an electrified way? Can we just make the molecules from the CO2 that we're breathing, turn them into hydrocarbons, into jet fuel, effectively a synthetic jet fuel, a renewable jet fuel, and then load the planes with that? And they emit the CO2, which we ultimately would capture and reprocess to convert it back into fuels using renewables. We're also doing the same with ammonia, where we're trying to, ammonia is where we started today's seminar. And ammonia, again, we get it from typically natural gas, where we strip the hydrogens off of natural gas and then use that to hydrogenate N2 that we're all breathing to make NH3. This is an electrified process that basically does the same thing, although in this case, we're going to grab our hydrogen not from natural gas, but we're going to grab it from water, which is a much more sustainable process to do so if you have renewable electricity to power it in the first place. So we've been making some progress along these fronts as well. So with that, I'm going to go ahead and conclude, and I'm going to thank you for letting me take you on this journey of sustainability and energy and health and all these challenges and all these interconnectivities. This is my team of researchers that has contributed to the research that we do in our group, as well as some of the funding agencies, and particularly the U.S. Department of Energy has been a very strong partner in all of this. And with that, I will go ahead and wrap up and leave you with this slide with possibilities for the future. I'd be happy to take any questions. Thank you all once again for inviting me to participate.
Thank you. And we do have some questions coming in for you. The first is from Lisa. Which countries are doing the best job in reducing fossil fuel use production? What can each of us do to do our part to not contribute to global warming?
Super. Yeah, that's a great question. I think, Europe has really been ahead of the game compared to the rest of the globe when it comes to the legislation that they've been putting into place and drivers. I have to say that the Scandinavian countries have taken it a whole nother notch. There are advantages to being a small country like a Denmark or a Norway or a Sweden. There's a lot of wind out there. Norway has a lot of hydropower, but it's beyond the resource that they have. It's really the commitment that the public has to being sustainable. And so there are partnerships that are formed in the Scandinavian countries where this industry and academia and government and the public are all highly aligned on that mission. And they've been progressing, I would say, faster than any other region on Earth than I can think of. There's a couple things to note. Number one, there are countries, let's say, so the United States, obviously a very big country, and we're cranking out a lot of oil, a lot of natural gas. We're also pretty aggressive, I would say, on the renewables. It could be more aggressive, but those are getting deployed pretty well. China is actually not terribly different. On the one hand, yes, they're still building a lot of coal-fired power plants, but they're also building a lot of photovoltaics. And in fact, they are the number one producer of global photovoltaics. So that's been very good for sustainability across the globe, including high power transmission lines to get their electricity going from the west, which is where their solar and wind resources, to east, which is where their population centers are. So even for countries I guess one way to also respond, I think Scandinavia is probably ahead of the game when you add it all up. Even countries that might not have such strong sustainability presence, you might not think of it, actually do have in some cases some pretty large active projects. But again, until the whole globe gets on board and really makes that the number one effort, it's going to be really hard to solve this challenge without global commitment.
Okay, thank you. And a few more questions. Can you speak a little bit about what Stanford Medicine is doing to reduce our impact?
I do not have the answer to that question. That's a great question. I'd love to learn from any of you who might have the answer. I think when it comes to sustainability, I think all of us as individuals and us as organizations, there's definitely things that we can do at all levels, right? So whether it's the building that we work in, whether it's the department or unit that we're part of, or whether we look at the whole School of Medicine or we look at Stanford. Now, Stanford, has done a couple of things that might be worthy of note. Number one, building out solar farms out in the Central Valley. So on average, Stanford is net zero on electricity. If you look at all the renewables that are online in the Central Valley and cranking out electricity, and you compare that to our annual electricity consumption, though it is not hour by hour net zero. And so we definitely consume our fair share of conventional power here on Stanford to keep the lights on. But we've deployed a lot of photovoltaics out there. Another thing is the Stanford Energy Systems Initiative, SESI. Some of you might have seen this on Stock Farm. Just off of Stock Farm, there's this really large facility. It's by the O'Donoghue Farm, where that is a way, there's basically these massive tanks of water. And it turns out that on Stanford campus, some buildings need heat at the exact same moment as some buildings need cooling, depending on how those buildings are used. Office space versus lab space versus a bunch of servers, for instance, they all have different requirements. And so what the university invested in was a system to move water around, and through heat exchangers in this large facility off of Stock Farm, they can basically move that fluid and in a much more sustainable way. So that saves a lot of energy, and it saves a lot of water use as well on campus. So Stanford's certainly been doing its thing, and I'm sure there are a lot of initiatives happening within the School of Medicine. What I wanted to really bring to everyone's attention is that at the end of the day, we can do all of that, and we should do all of that but we have to think beyond that. And how can we be more sustainable as health professionals, as engineers, the disciplines itself, the education in that discipline? How can we be adaptable, knowing that climate change is going to cause all these risks, and it's just going to, how can we be prepared for that, get ahead of that, and in the meanwhile, kind of design and innovate for sustainability? So it's not just what we're doing today, but what we want to do in the future. We need to think about the big ticket items. We're really, where there's perhaps a bigger lever. That being said, all the decisions we make at the individual level, at the organizational level, are still very, very important.
Okay. So another question, maybe you'll be able to answer it then, is have you considered using the waste gases released from hospitals and capturing them to separate nitrogen out of them to use as fuel?
Yeah, that's a great question. So, I think when it comes to, yes, we have a lot of emissions coming from point sources for a lot of different things, right? So it could be point sources from a power plant, point sources from a hospital, point sources from a cement factory, from a plastics facility, et cetera, et cetera. There are many different point sources, and it makes a lot more sense, generally speaking, to capture things at the point where it's emitted, as opposed to once it gets diluted in the atmosphere. So carbon dioxide is the classic example. Right now, the current concentration that we're all breathing right now is approximately 420 parts per million, where, it used to be historically around 270 and then climbed past 300, 350, 400, now 420. We're going to zoom past 450, maybe 500. And these are all very scary numbers from a climate perspective. That being said, if you're a separations engineer and you ask somebody to, can you please separate out for me 420 parts per million of this molecule versus the rest? That is extremely dilute. And that is a massive challenge. Methane's even worse. So methane has about 30 times or more of the global warming potential of CO2. And the concentration of methane in the atmosphere that we're all breathing is about 1.7 part per million. It's a factor of 100 less than CO2. So it's even harder to capture. And so getting things at the point source makes a lot of sense. With nitrogen specifically, nitrogen, because air is already 78% nitrogen, then that's already, you're starting off in a pretty good spot. And then oftentimes when we look at emissions coming from point sources, while they might be more concentrated, like the CO2 coming out of a natural gas power plant, for instance, it might be more concentrated at, say, 5% or 10% CO2, which is much easier to grab than 420 part per million. The problem there is that it comes with a lot of other stuff like, sulfur oxides and nitrous oxides and all particulate matter that are really impurities that can gunk up your technology effectively. So by no means am I saying that's a bad idea. It is a good idea to look at every point source. We got to recognize that there's going to be some trade-offs in kind of the cleanliness of their streams versus the concentration that we're after grabbing, and what the nature of the impurities are. Some impurities are more benign than others. So these are all important factors to think about. And I think this is where, if we, I haven't looked at this question specifically, but it's the nature of this question is inspiring to me, because it could be that there are effluent streams that are coming out of a hospital that are fundamentally different from other streams. They might be easier to use to do what you want to do. So thank you for that question. That's something that I'd love to look into. And if anyone has would like to share any more details on the effluents coming from hospitals or a reference, I would love to look into that more.
Thank you. I know we're getting close to time and it's a couple more questions, but maybe we can kind of take those and send them to you and your team, Dr. Jaramillo, for answering.
Happy to do so.
Get back. Okay, great. It was a pleasure having you. We were all very interested in this topic, and it's very meaningful, all of us. So thank you so much. And then we will follow up some of the questions that we weren't able to kind of get to today for your team's input.
Sounds like a plan.
Thank you.
Can we come off mute and give Tom a round of applause if everybody would do that?
Thank you all so much. Please feel free to reach out anytime. And thank you, Sabrina. If you don't mind emailing me those questions, and I can get back to you with some responses.
Thanks, everybody.
Take care. Thank you.
Thank you, Tom.